All right, so for the rest of the class today, I'm going to do a basics of electricity review. And I like to do this at the beginning of class because we're going to pretty quickly start to talk about, watts and volts and amps and electrical specifications. And so I just need to make sure that everybody's on the same page. If you're an electrician or you've taken a lot of classes, this is going to be sort of old news to you. But I just want to make sure everybody's on the same page with the terminology and some of the very fundamental calculations that you're going to need to be familiar with as we go through the class. Nothing complicated, just basic algebra, just to make sure that we're all on the same page here. All right, so electrical terminology. Electricity is energy resulting from charged particles. It's a dynamic flow of electric charge. That's probably the least important of these definitions, but I just had to put it up there. Current is the rate of the flow of electrons through a conductor measured in amps. So I'm going to use current and amperage interchangeably throughout the class. And when you see a spec sheet, we'll look at module spec sheets, we'll look at inverter spec sheets. You'll either see an I or an A depending on the specific context. It might say short circuit current, ISC is 9 amps, 9A. So we'll see either an I or an A, and that'll be referring to the current, which is the rate of the flow of electrons. And we'll look at a diagram in just a minute, and I'll talk a little bit more about what I mean by the rate of flow. All right, voltage is pressure or potential, and it's usually defined as the potential difference between 2 points, point A and point B. Current is the flow past 1 point in a conductor or a wire. Voltage is the difference between 2 wires or 2 points or 2 poles on a battery. You've got the positive and the negative terminal on your battery. If you want to know what the voltage of your battery is, you're going to measure the potential difference between those 2 points. And once again, we're going to look at a graphic, which I think is going to make this a little more clear if it's a little fuzzy in your head right now. Resistance is measured in ohms, and it's the material's opposition to the flow of electrical current, and it's just like friction in a water pipe, and it depends. You're going to have more or less resistance based on what type of material, what the diameter of the material is. We'll talk about wire gauges. The bigger the wire gauge, the lower the resistance. That's the bigger the diameter of the wire. Is it copper? Is it aluminum? Is it silver? Aluminum is higher resistance than copper. How long is the wire? Is it 20 feet? Is it 100 feet? A 100-foot wire is going to have more resistance than the 20-foot wire. Also, the temperature makes a difference. The hotter it is, the more resistance you're going to have. And so when we're building PV systems, we're going to try and have the least resistance as possible because this friction makes us lose power. It turns power into heat, and that's what we want to avoid. We want to keep all the power we're making with our PV systems. So we want to have low resistance conductors, low resistance systems. We're going to keep the resistance as low as we possibly can when we design systems. So I really like this water analogy. I think it's a really good intuitive way to think about the difference between volts and current and resistance. So if voltage is pressure, that would be like we've got tank A, we've got tank B. Tank A is totally full of water. Tank B is totally empty. So we've got a pressure differential here. And if we measure the pressure differential between tank A and tank B, it's going to be based on how much water there is in tank A. But to measure the pressure differential, we have to measure tank A and tank B, and we can measure what the pressure is between those 2 spots. And I think that if you think about it like a battery, you have to measure voltage between 2 different places to see what the potential electrical potential or electrical pressure is between those 2 points. So what happens if we open the valve in between these 2 tanks? The pressure causes the water to flow through this open valve. So the current is analogous to the gallons per minute of water we have flowing through this pipe that's connecting the two tanks. So something interesting to think about there is, what happens when the two tanks even out? Is there any flow between those two tanks? No, because there's not any pressure. So can we have electrical current if we don't have any pressure? And the answer is no. So voltage is the thing in our electrical systems that makes the current happen. If you've got a point A and a point B, let's say you got a dead battery. You measure your dead battery, you're measuring the voltage between the positive and the negative terminal on your battery, and you got nothing. Your meter saying 0 volts, you got a really dead battery. You don't have any pressure, so if you hook up a load, if you hook up a light bulb to that battery, nothing's going to happen. You're not going to get any current flow, and your light bulb's not going to light up because you've got no pressure there to make the current flow. So when we talk about voltage in a PV system, we're going to have voltages that we need to create. The PV modules are going to be wired together to build up this pressure so we can get the current to flow through the load, through the wires, to give us power. So, you know, I know a lot of people don't tend to think about electricity this way, but I think it'll help you as you go through this class if you think about volts as pressure and current as the flow. You know, one of the other things when we talk about choosing the right type of wire, you know, if you've got a wire, there's a little wire just hanging out on my desk, wires have an insulation, right? Plastic insulation on the wire. And, you know, why and how? Who decides how thick this insulation is or what type of insulation it is? Well, the job of the plastic that covers your wires is to stand up to the pressure of the voltage. So when you pick a wire, it's going to say 300 volt wire, 600 volt wire, 2000 volt wire. That's a voltage rating that's printed on every piece of wire that you buy, because that plastic insulation has to be strong enough to withstand the pressure that you're exerting inside the conductor from the voltage on the system. So if I'm building a PV system and it's going to operate at 1000 volts, I have to make sure I buy a wire that's rated for 1000 volts. Otherwise, my conductor will spring a leak. And that's not good when you've got water, and I think it's even worse when you've got electricity, because if you spring a leak in your wire, you're going to start a fire, or you're going to electrocute somebody. And so neither of those are good things. And so when we are choosing equipment for our electrical system, we have to be very careful that all of our equipment has the right pressure rating for the voltage in the system. And PV systems are interesting because, you know, you might have a 12 volt system, a 24 volt system, a 600 volt system, a 1000 volt system. It's all going to depend on how we wire up the PV modules. And we need to choose the other pieces of equipment in the class based on that pressure that we're building up. So we're going to pick a voltage for our system. We're going to design the system to operate at that voltage. And then we're going to choose wires and fuses and breakers and switches to be able to handle that amount of pressure. And we'll talk about current too. You know, current's also important, but I think if you start thinking about voltage and how do we build the voltage in the system, how do we get the right equipment, it's a good way to start thinking about different voltages in PV systems. So resistance is the size of the pipe between the tanks. Is an analogy for what resistance is. You know, the bigger the pipe, the lower the resistance. The bigger the wire gauge, the lower the resistance in the system. Okay, so what do we do with our volts and our amps? We're going to make power. So power is measured in watts, or W, and watts equals volts times amps. So as I mentioned, if we don't have any voltage, we don't have any pressure, we've got 0 volts, we don't have any power, we're not going to have any current, we're not going to have any amps flowing if we don't have any volts. 0 volts times 100 amps is 0 watts. So we have to have pressure to make our current flow so we can get power out of the system. So power is the rate at which work is being done, and it's an instantaneous rate of generation or consumption. And I've got a graphic I'll show you in just a minute to talk about that. So there's something else that a lot of people get confused about, which is the difference between power and energy. So we'll talk a lot about that here. It's really critical that you are very clear on the difference between power, which is an instantaneous rate of generation or consumption, and energy, which is a rate over time. So power equals volts times amps, watts equals volts times amps, amps equals watts divided by volts, volts equals watts divided by amps. You can change that equation around however you need to. And if you've got two of those factors, you can always find the third. There's just an example down here. 120 volts times 2 amps equals 240 watts. So if you think about your house, you plug something into the wall, that's 120 volt outlet. And 240 watts, what would be 2 amps? Maybe like, I don't know, a big computer monitor might draw 2 amps. Light bulbs don't usually draw that much power, especially good light bulbs. Maybe a desktop computer, maybe a ceiling fan, a pretty energy hog ceiling fan running at 120 volts will pull 2 amps. So the instantaneous power draw of your computer monitor or your ceiling fan, if it's drawing 2 amps of current, its power draw would be 240 watts. And we'll look at a lot of different illustrations of power draws. It's such a touchy thing. Sorry about that. Let me go back one more. All right. So down at the bottom of the screen, there are some conversion factors that I wanted you to know. 1 kilowatt equals 1,000 watts. 1 megawatt equals 1,000 kilowatts. And why that's important is because a lot of times people talk about PV systems in terms of kilowatts, watts, or megawatts. I'm working on a 2 megawatt PV system design right now. I'll show you an illustration of exactly what that means before the end of the class today. So it's easy to convert if you're converting from watts to kilowatts, you just move the decimal over 3 places to the left. If you're converting from kilowatts to megawatts, you do the same thing. You just move the decimal over 3 places to the left. It's not super critical to know these other conversion factors, but a horsepower is 746 watts. If you're doing something like putting in a well pump, you'll see that they're often rated as a 1/2 horsepower or 3/4 horsepower. It's a motor rating for a well pump. And there's also a BTU per hour rating. Not critical, just wanted to throw it up there in case you're doing something with like a solar-powered well pump. You'll often run into those horsepower ratings. Okay, so there's a light bulb over here on the right side of the screen. And if we were all in a classroom and not online, I like to think about watts in terms of like the lights in the room. So if you turn the lights on, there's an instantaneous power draw. Let's call this a 60-watt light bulb. So it's on 60 watts. It's off 0 watts. Like 60 watts, 0 watts, 60 watts, 0 watts. Wattage is instantaneous, and if your light bulb is off, there's 0 watts. If you just turn it on for a very brief second, you're pulling 60 watts, and then you turn it off again, you got 0 watts. So it's an instantaneous measurement of either generation or consumption. So that's different than energy. Energy is what happens if we leave the light bulb turned on for an hour, and it's a 60-watt light bulb. If we leave that light bulb on for 1 hour, then we've consumed 60 watt-hours. It's power times time. So power, you see watts or kilowatts. Energy, you're going to see watt-hours or kilowatt-hours. So what does your electric bill say? When you get your electric bill at the end of the month, it's not in watts unless you're an industrial facility, and we're not going to go there right now. Your power bill is in kilowatt hours. The utility is charging you based on your energy consumption. And for most residences, they couldn't care less what your power draw is at different times of the day. What they're looking at is your cumulative energy consumption in terms of kilowatt hours, which is the power draw rate times the time that you're using that power rate. So it's a measure of energy production or consumption. So we've got 60 watt, if we leave that light bulb on for 10 hours, and it's a 60 watt light bulb, 60 watts times 10 hours is 600 watt hours. So that's the energy draw of that specific power consuming light bulb if you leave it on for 10 hours. And we'll look at a couple of PV examples here in just a minute for PV system consumption and production. And stop me if you've got questions. This is pretty basic stuff, but you'd be surprised at how many people get confused about the difference between power and energy. I see a lot of articles in the paper where those two terms are hopelessly confused, so it's good to be very clear on the difference between power and energy. All right, so AC and DC, direct current and alternating current. Direct current is what PV cells and modules make. Alternating current is what our utility provider provides to our houses. And I like to say one is not better than the other. They're really not even that different. On some level, it hardly makes a difference, except that because PV modules make direct current electricity, we're going to have to convert that, and we'll talk about inverters on Thursday. We can't hook up a PV module directly to a utility grid supplied house without some power conversion equipment in between the two, because we have to convert DC into AC to be able to provide power to the loads in our house or to send power back out to the utility grid. If you look at those diagrams over on the right side of the screen, let's look at the bottom one first. If you look at the alternating current, that's a sine wave. And the sine wave is, when people say 60 hertz or 50 hertz, what they're talking about is how many complete sine waves there are per second for alternating current. So here in the US, we've got 60 hertz power. In Europe, they've got 50 hertz power. That's just a measure of how many sine waves, this complete sine wave, this red line there are, per second in the power that's provided by the utility generation source, and it has to do with the turbines and how fast they're spinning. So what's going on with this sine wave? This black line on this chart is meant to depict 0 volts or 0 pressure. So what happens with the sine wave is actually sort of interesting. The voltage goes up and the voltage goes down, and the voltage goes up and the voltage goes down. And that's why it's called alternating current, because both the current and the voltage follow this sine wave up and down, up and down, up and down, where they actually are sort of going positive, negative, and they travel through this 0 voltage point, which is it's a little bit hard to intuitively grasp, what the heck's going on here and why. If you could slow this down, 60 hertz is, that's very rapid movement of this current in sine wave. If you could slow it down, you might actually see a flicker. Like if you're looking at a light bulb and it's being supplied by alternating current, what's going to happen is there's this very brief moment in time where the voltage actually goes to 0. There's 0 pressure as we switch from the positive to the negative. So you might actually see a slight flicker. You probably wouldn't see it, but you could. If you could slow this down enough, you might see a slight flicker in your bulb because there's actually 0 pressure at every intersection of this sine wave with this black line, which is the 0 volts. The real difference is that with DC direct current, it doesn't go up and down like a sine wave. It's just unidirectional, one direction current flow. The voltage is just fixed, 24 volts, 600 volts, 1000 volts, whatever it is. It's not following that sine wave path. So when we convert DC to AC, what we're doing is we're taking that straight line and we're going to force it into a sine wave. We're going to put steps in that straight line to force it to look like and act like an AC sine wave. So that's the conversion process that we have to do with the electricity that comes out of a battery or that comes out of a PV module, it's always DC, and how we convert it and where we convert it, there's a lot of different options, but we have to make that direct current into alternating current to be able to feed it back into our houses and into the electricity grid. And we'll talk a little bit more about AC and DC later in the class, but mainly you just have to be aware that PV modules and batteries produce DC. In our houses, we're using AC. You know, everything being supplied by the utility grid around the world is alternating current. All right, we're going to do a couple of power and energy calculations, and then we'll pretty much be done for the day. But we're going to look at energy consumption for electrical loads, energy production from PV, and we'll do a couple of battery storage examples. All right, so here's a practice question. We've got 5 PV modules. They're shown down here at the bottom of the screen. That's a PV panel, PV module is what the correct terminology is, PV module. So a PV module with each panel, we've got 5, and they produce 8 amps and 30 volts at full sun. That's what we would call their nameplate rating. When you buy a PV module, that's going to be the specs on the spec sheet, their full sun power output. So how much power would these 5 modules produce under full sun conditions? Well, I gave you part of the answer down here already. To figure out the power for each module, that's going to be the nameplate rating on the module. We just multiply 8 amps times 30 volts. 30 volts times 8 amps equals 240 watts. So each one of these PV modules is a 240 watt module. So when you buy a 240 watt module, a 300 watt module, what that's telling you is it's a power rating for the module. It's not telling you anything about the energy that that system is going to produce. It's just a factory nameplate power rating for that module. So what about the 5 modules altogether? It's pretty easy math. 5 modules times 240 watts equals 1,200 watts. So we're going to call this a 1.2 kW array. Oh, that's what John said, 1.2. So John, you actually said 1.2 kWh. So that's, don't forget that's energy, and we're just talking about power right now, and power does not have a time component to it. So when you buy a PV module or you buy a PV array, you're buying it based on a power potential. We don't know anything about the energy yet. So this is just the power rating, the nameplate rating of the array. So what about energy? Well, if we look at the energy, we have to know something about how long the sun is shining. So we've got these 5 PV modules that produce 30 volts and 8 amps at full sun. How much energy are we going to make if these modules are installed in a place where they get about 5 hours of sun a day on average, or one day? You know, we're going to do different calculations throughout the course of this class. But to figure out the energy that a PV system makes, we need to know something about the location, the direction they're facing, how much shade they get. Is it a rainy place? Is it a very sunny place? You know, how much sun do we expect to get per day? And that's usually called peak sun hours. And we'll talk about where to find those numbers and how they vary from place to place. 5 hours just happens to be the average for North Carolina, and a lot of the Southeast is 5 hours of full sun a day on average throughout the year. We'll talk a lot more about that next week. All right, same calculation. We've got 240 watt modules. We've got 240 watts times 5 hours of peak sun a day is 1,200 watt hours per day per module. We've got 5 modules. We're going to multiply 1,200 watt hours a day times 5 modules. We get 6,000 watt hours a day from this PV array. That equals 6 kilowatt hours a day if we get 5 hours of full sun. And that number is going to vary every day. You get rainy days, you get cloudy days. We can look at average. We'll do a lot of calculations based on peak sun hour values throughout this course. What we're trying to figure out is, given a certain module with a certain power rating, a certain number of modules installed in a particular location, how much energy is that system going to produce on average or throughout the year on average per day. So we've got 6 kilowatt hours per day. There's a little asterisk down here that says note actual energy production value would be lower due to system inefficiencies. This is DC kilowatt hours, and as I said, we're going to have power conversion. We got wires, we've got resistance, you know, we've got some loss factors that we'll have to take into account. So would we really produce 6 kilowatt hours a day on the AC side of the system? No, it would be a lower number because we're going to lose a little bit of energy in the power conversion processes that have to happen with this system. All right, that was production, and we're going to do a lot of production analysis in this class on different systems in different places. We can also look at consumption. So if we've got a 120 volt ceiling lamp that has 4 100-watt light bulbs, how many amps would it draw? That's a question about power. How much energy would it consume if it was turned on for 4 hours? So first we're going to look at power. Amps times volts equals watts. We've got 4 100-watt bulbs. It's operating at 120 volts. That's our pressure. Amps times 120 volts equals 400 watts. We can divide watts by volts. We've got a 3.3 amp power draw for this ceiling lamp. And how much energy would it consume if we leave it turned on for 4 hours? We've got 400 watts times 4 hours is 1,600 watt hours or 1.6 kilowatt hours. That's the energy consumption of that lamp. All right, so nobody uses incandescent light bulbs anymore. I think they're illegal. I don't know if they stopped selling them entirely. So what if we replace our high energy consumption light bulbs with energy efficient compact fluorescent light bulbs? What if we have 4 15-watt CFL light bulbs? We'll do the same calculations with energy efficient light bulbs. 4 times 15 watts, our total power draw now is only 60 watts, which is going to take our current down to half an amp. So we've got a much lower current draw for the ceiling lamp now that we put in these energy efficient light bulbs. It's also going to really pull down our energy consumption. 60 watts times 4 hours is 240 watt hours or 0.24 kilowatt hours. So, you know, I think one of the things to think about here is if you're producing your energy from a PV array, what are you going to do with it? Do you want to feed it to energy hog devices? No, PV is not, it's cheaper, but it's still pretty expensive. Or do you want to make the best use of your energy with energy efficient appliances, energy efficient light bulbs? You know, there's a direct correlation here between how much you're producing and how much you're consuming and how much of your bill you're going to be able to offset with a certain size PV array. And, you know, a lot of customers don't particularly like to talk about energy efficiency, but I do think it's a valuable conversation to have with people. You know, if people have got 60-watt light bulbs, maybe it's time to replace those with LEDs or CFLs. Well, I would just say it is time to replace those with CFLs or LEDs. You know, it does make a big difference. It's not the major power draw in most people's houses. You know, the thing that uses the most energy in most people's houses is the HVAC, refrigerator, and the water heater. But lighting is still a pretty big load, and it's low-hanging fruit, as people like to say. All right, one more question, a battery question. How much battery storage in amp hours would be required to run a 15-watt, 12-volt light bulb for 8 hours? So batteries are a little funny, and most battery manufacturers don't talk about watt hours. They rate their batteries in amp hour capacity, and we'll talk more about this in week 5 and 6 of the class. So let's see. So once again, amps times volts equals watts. We've got 15-watt light bulb. It's running off of 12 volts. It's a DC light bulb. We can connect it directly to our battery. To figure out the current draw, we're going to divide the watts by the volts. It draws 1.25 amps for that DC 12-volt light bulb. 1.25 amps for 8 hours is 10 amp hours. So we would need 10 amp hours of battery storage to be able to keep that light bulb, that 12 volt, 15 watt light bulb, turned on for 8 hours. So we'll come back and we'll do more battery calculations later on in the class. I just wanted to throw that one out there because same math, same numbers, amps, volts, and watts. These are easy calculations to do once you get the fundamentals set in your head. All right, so this is the last slide for the day. And David Del Vecchio, who I think some of you will meet if you're taking the hands-on lab day, he'll be the teacher out there. He really likes to talk about, what is a kilowatt hour? We use a lot of kilowatt hours in our daily lives, but it's really a remarkable amount of energy. The going price for a kilowatt hour from the utilities is 10 cents in most parts of the country. Yeah, it's more expensive in Hawaii, but they've got to import all their fuel. 10 cents is the average price, in North Carolina and a lot of southeast states. So 10 cents a kilowatt hour. So it can run a 25 watt light bulb for 40 hours. That costs 10 cents. But what is that in human terms? Well, a kilowatt hour equals 2,600,000 foot-pounds, which would be like lifting a ton 1,300 feet high. So what would someone charge to carry 9 94-pound bags of concrete up a 3,000-foot mountain? They would definitely charge more than 10 cents. And there's a lot of energy embedded in a kilowatt hour. So if a Nepalese Sherpa carried your 90-pound backpack from sea level to the top of Mount Everest, that would be a kilowatt hour of work. So, kilograms. Larry says this was kilograms.
Yeah, we actually had our Nepalese physicist. He saw that and he was like, wait, no, I know. So he did a manual calculation. He said like, oh, then instead of 90 pounds, it should be kilograms. So the whole metric system conversion.
That's heavier.
Well, we actually had a Nepalese Sherpa calculated.
It's still, it's actually heavier a kilogram than a pound, but that's just, it's kind of an astonishing amount of energy, and we sort of totally take it for granted. And even PV modules now, the 300 watt PV modules is sort of the going size, and 3 hours with a 300 watt module, you've got a kilowatt hour. It's pretty amazing, and a 300 watt module may cost, $250 now. Anyway, we'll talk more about prices and energy, but it's not something to scoff at. There's a lot of energy embedded in that 10-cent kilowatt hour. So, all right. Well, I hope you enjoyed the first day of class. What we're going to do on Thursday is take a closer look at system types, the different types of PV systems, and the components that go into those different types of PV systems. And we'll talk more about metering setups, like what does it mean when you net meter, what's the interaction there with the utility grid, and we'll talk about different types of battery-based systems too, just basic components, basic system diagrams, and a few more industry statistics as well. All right, well, I appreciate y'all joining me for the class, and let me know if you've got questions. You can email them, you can type them into the chat box, you can post them on the forum. But I appreciate y'all joining us for the first day of class.
Great, thanks everyone.